Hi there everyone. We use copper and gold everywhere in FPV, from motors to flight controllers and ESCs and a host of other electronics. And it's no wonder, copper and gold are some of the most conductive metals, but they're not the most conductive metal. That title belongs to silver. In this video, we're going to be looking at why copper, silver and gold are such conductive metals, why silver is the most conductive, not gold, and why we don't use silver more in all of our FPV components. It's a lot to cover in one video, so let's not waste any more time. Let's dive right into it. Before we can talk about why copper, silver and gold are so conductive, we first have to understand a little bit about how conductivity works in metals. In metals, multiple metal atoms come together and lose their outermost electrons to form positively charged metal ions in a sea of delocalized electrons. These delocalized electrons hold the metal together, and they are also able to move freely through the material to carry heat and electricity. The more easily these outer electrons are lost from the metal atom, the more freely they are able to move through the whole structure, and then the better they're able to carry heat and electricity. So conductivity in metals primarily depends on how easily the outer electrons are lost from the metal atom and how easily they can therefore flow through the material. If we look at a periodic table, we can get a clue as to why copper, silver and gold are so conductive. They all appear within the same column in the periodic table, in the group of transition metals. And when we have multiple elements in the same column, we can be confident that they all have very similar configurations of their outer electrons. And it's that configuration of the outer electrons which is primarily responsible for why these materials are so conductive for heat and electricity. To understand why some atoms are able to lose their outer electrons more easily than others, we have to look at the electronic configuration of the different elements. And for this, we're going to look at the periodic table. And I like to think of the electron configuration of atoms like a parking structure with multiple levels. And within each of those levels, we have multiple zones or orbitals, each of which can hold different numbers of electrons. As we move across and down the periodic table, we fill up these electron orbitals or zones in our parking structure one by one. So starting with the first level of the parking structure, we have a zone there called the s orbitals, and the s orbitals can hold 2 electrons. And that's why we have 2 elements in the first row of the periodic table as we fill the 2 spaces in that s orbital. When we move down to the second row of the periodic table, we move up to the second level of our electron parking structure. And in the second level, we have 2 different zones. The S zone again, which can hold 2 electrons. So we fill that up as we move from lithium to beryllium. And then we have a second set of orbitals called the p orbitals. The p orbital can hold 6 electrons. And as we fill it up, we move from boron all the way across to neon. Then we go to the third row of the periodic table and up to the third level of our electron parking structure. And again, we have 2 zones, the S zone and the P zone. And we fill them first the S zone and then the P zone as we move from sodium all the way across to argon. When we get to the 4th level, everything changes. Initially, we start to fill the 4s orbital just as we did before. But then, because the atom has gotten bigger and the positive charge on the nucleus has gotten stronger, we're suddenly able to push more electrons into the 3rd level. And we open up a new zone of our parking structure, the d orbitals. And we start to push electrons into those 3d orbitals. And those 3d orbitals sit below the 4s orbital that we've already filled. So it's like we're sort of pushing electrons down into the 3rd level whilst leaving the 4th level undisturbed. And as we move from scandium all the way to zinc, we're filling those 3d orbitals. When we get to nickel and copper, something really interesting happens. If we look at the difference in electronic configuration between nickel and copper, we can get an insight into why copper and silver and gold are so conductive. Looking at nickel, we can see that we have a full first shell, a full second shell, and the 3rd shell, the green shell, is partly full. You can see that we have 16 electrons in that shell, and we can fit a maximum of 18 electrons into that 3rd level in the S, P, and now the new D parking zones or orbitals. The 4s orbital, which can hold 2 electrons, is also full in nickel, and we haven't started to fill the 4p orbitals yet. So those 4s orbitals just around the very outside in orange are full, and we haven't started to fill p yet. If we look at copper, we can see that we've pushed 1 extra electron into that 3d orbital. So now we have 17 electrons in the 3rd level, and the 4th level again, would be full. Those 4s orbitals would be full. But in copper, something really interesting happens. One of those outermost electrons in the 4s orbital gets ripped and pulled into the 3d orbital to make sure that third level is completely full. Electron shells love to be full. So if there's only one gap left, there's a really strong pull to try and fill that final gap and have a completed third level. And so it does that. It pulls one of the outer electrons from the 4s orbital into the 3d level. And now we have full first, full second, and full third level, and then one lone outer electron in the 4s orbital. So there's only one electron in that fourth level. And that is what makes copper so conductive. It's got that one lonely outer electron in the fourth level, and it's very easy for it to lose that electron. So when it becomes a metal, it loses that outer electron super easily, and that outer electron is very free to move easily through the metal and carry heat and electricity really, really well. So now we can understand why copper, silver, and gold are so conductive. But why is silver the most conductive? Let's compare the electronic configurations of these three metals to see why silver is the most conductive and why gold and copper are less so. The difference in conductivity between copper, silver, and gold is explained by another property called electronegativity. Electronegativity is basically how strongly the atom is able to hold on to its outermost electron. Now, both copper, silver, and gold have a single lone outer electron, so the electronegativity of the atom determines how easily it's able to lose that outer electron and how easily that outer electron is able to flow through the metal to carry heat and electricity. Electronegativity is determined by two things. The first is the positive charge on the nucleus. The larger the positive charge on the nucleus, the stronger it holds on to electrons and the higher the electronegativity. So, all things equal, an atom with a larger nucleus and a stronger positive charge is going to hold on to its outer electrons better, and that means that the metal will be less conductive. The other aspect of electronegativity is the distance of the outermost electrons from the nucleus. The further away the outermost electron is from the nucleus, the less strongly the atom holds onto it, the easier it's lost, and the more conductive the metal will be. When we move from copper to silver, we add an extra shell of electrons, and that moves the outermost electron further away from the nucleus. And it turns out that that increase in distance has a bigger effect than the 18 additional positive charges on the silver nucleus. And that means silver is less electronegative than copper. It loses its outer electron more easily, and that makes silver an even more conductive metal than copper. When we move from silver to gold, the situation is reversed. When we move from silver to gold, the increase in positive charge on the nucleus of the gold atom is much bigger. We get 32 additional positive charges, and we only get one additional shell of electrons. So the outermost electron from gold is not much further away than it is in silver, but the positive charge on the nucleus is much bigger. So gold holds on to its outer electron a lot more strongly than silver. And actually, gold holds on to its outer electron more strongly than copper because of that extra positive charge. It pulls all the electrons in. For a more detailed explanation, we have to look at an extended periodic table. And an extended periodic table has the lanthanides and the actinides, these sort of pink and purple elements, in their correct positions. When we got down to copper, you remember I said that because the atom had gotten bigger and there was more positive charge on the nucleus, we were able to start pushing more electrons into the third level. Well, the same thing happens again when we get to the row with gold on it. On the sixth row of the periodic table, there's enough positive charge on the nucleus that we can open up a new zone on the fourth level of the electron parking structure, called the f orbitals. And we can start pushing more electrons down into those f orbitals. And in fact, those f orbitals can hold 14 electrons. And so that means we can have a much larger positive charge on the nucleus, balanced by additional electrons being pushed down into the fourth level. And then we don't need to add extra electron shells that would push the outer layers further away. So that means that gold is able to fit 79 electrons into only 6 shells, only 6 levels of the electron parking structure. And that means that the outer electrons are closer to the nucleus than they would otherwise be. And that's what allows gold to hold onto them more tightly and end up being a bit less conductive than silver. If you love these kind of deeply scientific explainer videos, why not hit the like button and subscribe to the channel to make sure you're among the first to see new videos as soon as they're released. So what's the result of all this? Well, silver is the most conductive metal, and in fact it's the benchmark for conductivity, and it gets a rating of 100. Compared to silver, copper has a conductivity of 97, so it's 3% less conductive than silver, so not much different really. Gold only gets a rating of 76. So gold is significantly less conductive than silver and less conductive than copper. So if gold isn't that conductive, why is it used everywhere in electronics? Well, it's the corrosion resistance of gold that is highly prized here. Gold surfaces don't corrode when exposed to air, they don't form an oxide layer. And so when you bring two gold surfaces together, you get a clean metal to metal contact with no oxide layer in between. And that allows electricity to flow very easily. We use gold very sparingly, so very thin plating, and that's partly because gold is expensive, but also because by having only a very thin layer of gold, the slightly less conductive nature of gold doesn't really impact the performance of the electronics at all, because you've only got a very thin layer of gold and then you're back into copper, which is much more conductive. Why don't we use silver more in electronics? Well, partly because silver is very expensive compared to copper, and it's not that much more conductive. And similar to copper, silver forms an oxide layer. And although silver oxide is conductive, it's not as good a conductor as a gold contact. So gold-plated copper is generally preferred as it gives the best balance of conductivity, cost, and excellent contact performance as well. And that brings us to the end of the video. I hope you enjoyed this scientific deep dive on the conductivity of these three different metals and what makes them so useful for our electronics in FPV. If you enjoy videos like this and you want to support the channel and help me make more videos, then please consider joining my Patreon. You can join from just a few dollars a month. You'll get access to a special area of my Discord server, and you'll also have some sneak peeks of some new products that I'm working on and the opportunity to make sure that you can order them before anyone else. That's all I have for you for today. So until next time, I wish you all very, very happy flying.